today we are on Unit 12 of chemical. Today we're going to move along to another. We've been dealing with KC for concentration, KP for pressure, equilibrium situations. We talked about an ice chart. It's used. We talked about how to utilize that equation in regards to using K concentrations or pressure, depending on if it's KP. In regard to a situation where I have equal, remember when K, so with an initial values, still we were able to determine based on quadratic formula. So today we're going to new K. KSP actually stands for soluble product, and why that's a very good name for it here in just a few minutes. So now we're going to this particular K deals with solubility, which is in representation and how as I look behind here, originally would have forth our students here behind for modified and that's located on the campus. So anyway, what do let me get rid of that and pull up our notes today. Okay, so we're talking now about solution chemistry, and solubility. I'm going to introduce KSP. So in our earlier discussion of standards in general, for predicting solubility in salt and water. Remember, we had things that were soluble and we had things that were insoluble. We had some rules there. Things that are all soluble. You know, we had group 1A compound. We had compound nitrate, acetate, ammonium. We had compounds that were mostly, a few exceptions, mostly insoluble exceptions. So covering all that was fine. Those rules give us a general idea as soluble a compound in water, but qualitatively. All right, only quantitatively or qualitatively. Excuse me. By considering an equilibrium, we can get a prediction about the amount of a given compound that will dissolve. Now, I'll get much more detail. When we were looking at solubility rules, they were either soluble or they were, cut and dry. Things that are soluble are not soluble in degree. All right, things that are insoluble doesn't mean they're not soluble at all. It means that they're soluble to a very, very small degree, but again, they're not all the same. This allows us to be much more specific quantitatively as to how soluble or how insoluble a compound actually is. So recall that a saturated solution is one in which there is a solid dissolving a given quantity of solvent at a given temperature. Remember when we were doing lab, all right? So we're pouring in a given water, and we started off very dilute, and it dissolved these. As the solution more and more constant, remember you add your Kool-Aid up a lot more, and it'll get dissolved. Now, if I remember correctly, even our fourth and last solution in water completely tough getting it to dissolve. So we were getting very, very close to the saturation point. And then some of you that after we did the solutions made some additional ones where you got it and ultimately exceed the saturation point undissolved. Now, if a saturated solution, okay, is in undissolved, you see the solution itself is more solute in there. That amount of solute is undissolved. An equilibrium is really established with undissolved, and those that have dissolved in water, and that's what hydrated means, solution. For example, so we have an equilibrium right here, solid calcium, and that dissolves. This dissolves with a little H2O up here. We don't need to do that now. We understand that it's there because over here our ions number split apart, which is what H2 drives itself in between those particles, and it's attracted to the negatives of them. Here are our ions in calcium ion, and you have two chloride ions, both in solution. So this is just ionization times before. One thing I want to bring up, so this is equilibrium reaction between and ions that have indeed dissolved based on the solubility compound. Recall, this is an important thing. Recall that solid substances are not included in the equilibrium expression as their concentrations are. Remember, you can derive the concentration of a solid based on two properties. One is its density, and the other is its molar mass. Put a little thing over here. That's 7 days ago. Review. So if we found density and divided that by its molar mass, which is grams per mole. If you divide grams per mole, it's the same multiplying by its moles over gram. Do that, and which is molarity. All right. So for a liquid, because vary with quantity, then so is the concentration of solid or liquid. So the concentration molarity is constant. Of quantity. All right. And that is why pure solids are included in a K expression. It's like whether it's KCP or now K either. So the constant dissolving of a site depending on the molar concentration of the ions that are in solutions. Okay, it only depends on, because the equilibrium expression to which the solid is soluble in water, the equilibrium constant is the solubility product constant, or K. All right, the degree to which the solid will. So K not quantitatively determine solubility. So now we have a mathematical way to compare the value of bonds in water. All right, their value of KSP is going to tell you. So whether something is soluble or not, well, let's say it is soluble. It doesn't mean it's exactly as another compound that is soluble. Maybe compounds you can dissolve if you put in whatever quantity of that compound in water, gram or every last particle dissolves, and another one, all the particles dissolve except, well, 99.99999% solid. We call that qualitatively solid, but the two solubilities are slightly different. Same with insoluble. All right. All right. We say rocks are insoluble. I mean, down to the shoreline where I live on a lake. Most of you, I think, know that. There's rocks sitting there forever, and it looks like they haven't changed yet. They're a fractional amount of salt water over the years. Would you ever notice the difference? The number as compared to the number of particles that haven't. It's so small in determining its mass. But every solid in some degree, or how small. All right, how small. This will give us an idea of how soluble something is, but how insoluble it is. All right. So the KSP reaction would then be simply, remember K, any K is product over reactants. But since our reactants is solid and the solids are included in the expression, we don't have a denominator. All right, so the K is simply the concentration of the ion times the concentration squared because of that. Right. All right. Let's go to the next page, and we will do an example. But before I do, I want to make sure you understand the value of K determines how soluble, or KSP rather, soluble something is. All right. So with this reaction you said a little bit ago, all right, it's an equilibrium dissolved ions. And KSP then at equilibrium, if we know this and we know this concentration and we do the math, we can get a value for K. Well, now let's take let's KSP, I don't know what it is. Let's just say it's 1.0 times 10 to the minus. Okay? So then let's say we have another one. We have another reaction. And KSP for one is 1.0 times 10 to the minus 11. Okay, well, all right, so this number in decimal place is this one. Well, what is that? Well, the K is only equivalent to the concentration of the dissolved ions, together, of course, then that means that if for this one here, these two concentrations are much, much greater, all right, than these two concentrations would be if it's another way of this value, which is smaller. So what does that tell you? Well, the larger the value of K, the larger the value of KSP, the more dissolved ions you have equilibrium. What does that mean? More dissolved is more soluble. So compound is more soluble. That's why SP is so critically important in regards to solubility. Its value, we can compare values of KSP for different compounds and say, oh, this one dissolves in water. Let's see, that's 10. Yeah, this compound dissolves in water 10 billion times. Nuts. I mean, eight decimal places is 10 billion, I think. Wait a minute, maybe not. A million six. 10, well, I'm wrong. It's 100 billion. My bad. My thinking ahead there went right. Yes, this place is a million, 8 decimals, 100 million. Compound, whatever K this compound represents, 100 million times more soluble in water than this one would be. Okay? That's what KC can tell you. All right. So let's look at our example here. In the saturated hydroxide, my notes are over here. The ions at equilibrium is 1.3 times a mole. First, write the equal equation. Let's see hydroxide in solution. Remember, dissociation is ion. So basically, we're going to dissolve it in water and ions. We have calcium hydroxide. And when we dissolve that in water, we normally use water up there. What does it dissolve into? I mean, what does this part into? Well, you got a calcium ion here, and we have 2 hydroxide. So there's our equilibration. All right. Writing expression for KSP. All right. So KSP, any other K is our reactant is a solid in there. Remember the constant. So our combination of calcium ions squared. T. Determine the equilibrium iodine. All right. We're going to need an ice chart for that. All right. So I'm going to go ahead and rewrite the equation. Okay. And we know that, look, we know that the constant of ions at equilibrium is 1.3 times 10 to the minus third. We know that. So I'll that down here. Calcium, 1.3 10 to the minus third mole. We know? Well, you know what? It's because what is the constant of our products initially? Yep, changed. It's 0. It is 0. Okay, well, we have, I'll talk about this one in a minute. We have 2 numbers in it. That is immensely helpful, all right? To get from 0 to 1.3, we have to add that quantity. And remember, prior also plus, and those disappear. So 1.3 times 10 to the minus 3. Okay. Now, well, whole ratio 1 to 2. This is going to be made or produced at twice the rate that calcium is. All right. One ratio there. So then the change in the hydroxylation would be 2 times in the calcium ion concentration. Put a C. So it would be 2 times 3 10 to the minus third. And so that comes out to be 2.6 10 to the minus third mole. Would be the change in the hydroxide. Again, mole ratio is what we use in regard to changes. All right. So equilibrium, there's that. Okay. So we haven't done a thing over here. Haven't done a thing. Key line. Oh, so we can answer the question here. Go ahead and do that. Equilibrium hydroxide ion concentration then would be 2.6 times 10 to the minus third. All right. 2 times 10 to the minus third. Which is right here. And again, I didn't around in our ice chart. We do here, but just for this particular one, number 6 exists too. So that's good. Another question is, what about? I haven't even looked at it yet. Well, let's remember something. Solids. Liquids are not used. All right. Solids are not used in a KSP because their concentrations remain constant. Regardless of quantity, the concentration is still constant. But are useful ratios. All right, so let's look at that. The concentration remains constant. Concentration then. If you said 0, you're right. It doesn't change. It doesn't change. So how do I know what it is? Mole ratio, my friends. What is the mole ratio between oxide and lithium ion? What is the mole ratio between hydroxide and hydroxide ion? 1 to 2. Is it here? So this would be the easiest way. This is 1, and this is 1 to 10 to the minus third. What does that make this one? Same. Didn't change at all. This concentration. Okay. Same. All right. Letter D, calculate KSP. All right. Well, let me see. Sorry, I'm going to have to erase all that. Anybody notice anything about the equation? We did. So if you're nodding now or saying, oh, "My goodness," you're not. I thought the same thing when I learned it. All right. So, Katie, yeah, no quadratic equation needed in KSP. All right, so KSP we wrote earlier is equal to the calcium concentration times the hydroxide concentration. And so calcium concentration for the chart was 1.3 times 10 to the minus third. The concentration was 2.6 times 10 to the third, and that is squared KSP to 6 times 10 minus 9. Not a big number or small number? Well, that's dang small. So what does that mean? Well, if you look back at your equation for Kx over reactants, I know we don't use the reactant in this one because it's a solid. But quantities, the concentrations at which ions in solution are quite small. If there aren't very many ions in solution, what does that tell you about the solubility of that solid? Well, it means it's not very soluble. All right? It means it's not very soluble. So hydroxide is not very soluble. Think back when we talked about moles. All right? Think about it. We said that most hydroxide compounds are not soluble. They're insoluble. All right? But a few exceptions. Ammonium, mainly, all right, of which has one K bears that out. Quantitatively, we just determined calcium hydroxide is not very soluble. All right, but now we know to what degree that it's not very soluble. Okay. All right. Okay. So that finishes today's lesson. But I want to pull up homework, which is equilibrium number 4. There it is. All right. I actually want to go through number 1 with you. All right. It deals with solubility. It's a lesson, and then the one in the notes. And so I wanted you to see how this is. Okay. All right. So we have solubility of in water is 0.0279. Right? Right. The equilibrium dissociation innocuous solution. So again, we're just writing the ionization of this solid water as it dissolves into ions. That. So equation. So we have silver chromate, solid, equilibrium with. Okay, so what is silver chromate split in? Well, we have 2 silver ions, which have +1, and we have a chromate ion, which has a charge of -2. So there's the equilibrium equation for the dissociation ionization. Based on its calculate the concentration which is a molarity. Okay, so this is talking in regard to the relationship between molar mass and concentration. So we have solubility 0.79 grams per liter. Is that very soluble? 0.029 grams of silver chromate in a liter solution. Is it much solid? No, it's not. Its solubility is quite low. So for all practical purposes, we would call this insoluble. But now we're going to solubility. So we're just going to use a little geometry with that, like I showed you a little bit ago. So I'm going to take it, so 0.029 grams of 1 liter, and I'm going to use its molar mass to get a molar liter, which is constant. So Ag2 is, let's see, silver 108. 32 grams per mole is its molar mass. Use that to cancel out the grams, right? So we have mole of silver chromate, 332 grams. With the units over here, you can see that we are left with moles per liter, which is molarity or molar concentration. Next out the three sig figs, 8.40 times 10 to the minus fifth molar. So again, that is concentration based on its solubility, its molar mass. Equilibrations of the aqueous ion. Okay, well, let me move this up so we have more room to work with here. I'll erase this. So we're going to find the concentrations of everything. So when I use an ice chart, so I'm going to rewrite it just a little easier. See what's what. We have two silver ion and CE. There we go. Now of our silver chromate in terms of determined up in, and that is 8.0 times. Okay, 8.40 times 10. Here, to 0. Remembering the concentration of a solid is constant, which means there is no change there. There is no. So at equilibrium, this is the same. It remains the same. Well, we can't utilize the change off of this one, but we utilize the mole ratio of substances down here. And this is like in the example, and that's exactly what we're going to do. These are the chromate and the chromate. It's all pretty simple. So we have the equilibrium concentration of the chromate ion would be equal to the equilibrium concentration of our silver chromate. It's the same value, 8.40 times 10 to the minus fifth. And so that would go right here. And of course, then the change would be the same. Now, as far as the silver, well, whether you're looking at this one here or this one here, it's 2 to 1. So silver's concentration is double that of the chromate, and it it should also double. All right. So the equilibrium silver ion would be 2 times the equilibrium concentration of either one of those, no matter which one you use. I'll stick with silver chromate. It would be 2 times 840 times 10 to the minus 5, which would then be 1.68 times 10 to the minus 4. Okay. I didn't round this, although it does come out at 2.6. We don't have to really worry about that. Here it comes out the same. So that would then go here. And also here. Okay? So the barium concentrations of chromate, silver. Okay? And then write equal expression for KSP calculated. All right? So KSP is products over reactants. So you are solids. Have you figured out why SP in the KSP means solubility product? Think about that. Let me write the expression here and we'll do it. We'll see if you can. Silver squared is the chromate. Solubility product. The thing reactant is a solid. All right. So all X are expression and the determination. All right. Solubility. All right. So silver ion is 1.68 4 paired chromate ion 8.40 times 10 to the minus 6. Here the solids value, the fact didn't change. This very, very helpful using mole ratios to those. Okay, and again, no quadratic formula needed either. So to 3.37 times 10 minus 12. 10 to the minus 12. All right, so in the note, the KSP that we determined for calcium hydroxide is 8.8 times 10 to the minus 9. 2.3 times 10. So give or take 3 decimal places. Like I said, it's not exactly because of that. Decimal places off approximately. All right, so we said hydroxide is insoluble. This one is even 1,000 times less soluble than it is, right? So obviously, qualitatively, they're both soluble, but now we know not both insoluble to the same degree. That's what KP tells us. That's what it tells us. The other problem on assignment 4, equilibrium number 4, similar to the one that we did. So I think you're good to go as far as your homework. And then the next that's also attached to this lesson is equilibrium number 5, which is a review of AC, KP, and now KSP. So you get equilibrium constants, situations where we're all equilibrium. Which in this chart, if you already have equilibrium numbers, But we've also dealt with a chart whereby we don't equilibriums, and sometimes we're able to get them without using the quadratic formula. We did that. And then the last lesson, I had to use to determine equilibrium. This assignment, equilibrium number 5, kind of sizes for everything we have done. So that is it for today. Until next time, continue on with our study of equilibrium. We have coming up next, and that'll be up here on our next video. And so keep plugging away at it, keep working, stay safe. I'll catch you next time. Take care.